Hey Geometry, in lesson 1 of unit 4, our curriculum takes a path of discussing programming a robot to sort of weave linear equations into geometry. I hope it makes sense. We're going to step through a few things, but we have a lot of linear algebra that we need to remember. There's some Khan videos that I've pulled together that I will distribute that I highly recommend you watch, because if you have forgotten or didn't really understand it the first time, all of the linear algebra stuff, equations of lines, slope-intercept form, etc., it's going to be to your benefit to go back and review it again. It's going to make your life easier. I'm not trying to punish you. I'm trying to make your life a little easier by refreshing your memory of stuff you've learned before. First of all, let's look at a robotics class. So students in a robotics class must program a robot to move about an empty rectangular warehouse. The program specifies a location at a given time t seconds. The room is twice as long as it is wide. Locations are represented as points in a coordinate plane, with the southwest corner of the room deemed the origin, or 0, 0. The northeast corner deemed the point 2,000, 1,000 in feet, as shown in the diagram below. The first program written has the robot moving at a constant speed in a straight line. At time equals 1 second, the robot is at position 30, 45. So if we went over 30, up 45, we'll just say it's right there at t equals 3 seconds. It's at position 50, 75, so a little bit further, up a little further. Oh, sorry. Let's reread that again. So at time 1 second, it's at location 30, 45, and at time 3 seconds, it's at position 50, 75. So it's 2 seconds have passed. So at what location will the robot hit the wall? I mean, we're linear here, so it's going to hit the wall somewhere up there. I mean, my line is estimated. It isn't a good line, but I can figure out when it's going to hit the wall pretty easily. Let's see, if we figure out the slope of that line, change in y over change in x equals, let's see, change in y is 70 minus 45, 75 minus 45. And change in x is 50 minus 30. 3/2 is my slope. Using a point slope form, I can figure out what my y-intercept is. I have a pretty good idea what it is, but I'm still going to calculate it just to make sure. I'm going to pick a point and a slope and plug it into y equals mx plus b. I don't know what b is, but I do know that 75 is y, m is 3/2, and x is 50 plus b. Half of 50 is 25. Three times 25 is 75, so b equals 0. So that thing goes right down and it starts at my origin. So my equation for this line is y equals 3/2 x. And I want to know what value x is when y is 1,000, because I'm pretty sure that we're going to hit our y value first. So 1,000 equals 3/2 times x. If we multiply each side by the reciprocal, these cancel out, and I've got 1,000 times 2/3. X is 666 and 2/3. So this answer for part A is 666 2/3, comma, 1,000. Cool? And I found that just by using my equation for my line. I guessed that I was going to cross the top of my warehouse, the north part. I was going to cross that first, so that's why I plugged this into my equation, y equals 3/2 x. I took that and I solved for x to figure out where my x value is when it crosses that, that spot of the building. So this point right here is 666 2/3, comma, 1,000. Now, if my x value would have been greater than given, I know I would have guessed wrong. So I would have had to try again. Cool? Let's keep moving. At what speed will the robot hit the wall? Well, let's figure out what speed it is at the distance. So this little robot covered a distance in 2 seconds. We deemed that it was 2 seconds, right? But we don't know the distance that it covered. I can use the Pythagorean theorem and the distance formula with that to figure it out. So I need to do my x2 minus x1 squared plus y2 minus y1 squared, given the 2 points in the problem. Let's see, I need those points back. X will be 50 minus 30, which is 20 squared plus, and then y is 75 minus 45, which is 30 squared. Get my calculator out. 20 squared plus 30 squared, 1,300. .1 feet in 2 seconds. So 18 feet per second is the speed at which the whole robot will hit the wall. It's going to hold that same speed the whole time, right? At what time will the whole robot hit the wall? Well, what's the total distance that we traveled? We went from, and we started at 30:45. So let's figure out this distance. Change in x. Squared plus change in y. Let me do my calculator real quick. Minus 30 quantity squared plus change in y. And then square root. I did a lot of that in my calculator, but you can work the problem yourself and make sure you get the same number. So that's your feet. I'm going to divide by my rate. 18 feet per second. And that gives me 63.8 seconds approximately. So these are very representative of problems you're going to have to hit in your problem set. So please, if something doesn't make sense, yell, and we can review it again in class. But it's going to be a lot of distance formula, and distance divided by time is rate, and distance divided by rate is time. What we see here, though, the time the robot will hit the wall, I said that it will take 63.8 seconds. This point right here was at time equals 1 second. We really need from time equals 0 seconds. So I can just add 1 second here, and my actual time is 64.8. seconds. You'll see at the end of this video, we calculate this again, but we actually use an ordered pair at time equals 0. So we know where that robot is at time equals 0. So I find the total distance from time equals 0 until it hits the wall, and then use the rate times the total distance to get the total time. But here we started calculating from time equals 1, which that ordered pair is, instead of time equals 0, which is no big deal. We just need to know what we're looking at and make sure we can figure out the correct answer given all the information we're given. Cool? Distance equals rate times time. Time equals distance over rate. Rate equals distance over time. All the things you need to know. All right, exercises. So plot the points on a coordinate plane. We did. Actually, I have a coordinate plane in my next slide. So what we're going to do here is we're not going to plot on this slide. I forgot. I put in a slide with an actual coordinate plane. These are all the things that we're going to work through. And it's the same exercise, just probably stepping through more of the steps in detail. We glossed over it in the opening exercise a bit. So now we're going to step through each thing. So I'm not going to work on this page doing each one of these, but you see these in front of you. You've got the classwork in front of you. You know what we're working towards. I've got these written down in front of me, but yeah, we'll work through them together. So let me graph it first. Still need to graph it. There we go. So first we're going to plot these points on a coordinate plane. I need to go by 5s, I think. This being 0, 0, let's do this. The warehouse is in the corner. 5, 10, 15, 20, 25, 30. That's not going to be enough. I need to go by 10s. 5, 10, 20, 30. 10, 20, 30, 45. That's terrible. I hate trying to make dots on this thing. So that's going to be 30, 45. And then we're at 50, 75. So 10, 20, 30, 40, 50, 10, 20, 30, 40, 50, 60, 75. So there's our points. Now step 2 says draw a segment connecting the points. Best I can do. So how much did the x-coordinate change in the 2 seconds? So that's our run. So our delta x, our change in x was 20. Let's see if I can get another color. Because the next one says, how much did the y-coordinate change in 2 seconds? That's our delta y. 30. What is the ratio of change in y to the change in x? So we can say either it's 30 to 20, which is 3 to 2, but we really don't like looking at things like that. This makes better sense. The ratio of change in y to the change in x would be 3 over 2. The equation of the line in motion, I can go down 30, let's see, 10, 20, 30 over 20, down 15 over 10, and make it back to 0. So I did start at 0. So that's where it says the ratio of change, that we just did that one. This was number 5. Number 6 was the equation, y equals 3/2 x, which is what I did in the previous slides, right? What theorem can be used to find the distance between the point? We would use the Pythagorean theorem. I would say d. D squared, well, let's keep it what we've always done, right? Pythagorean theorem says c squared equals a squared plus b squared. So my diagonal is c and my legs are a and b. C is really the distance between the 2 points, which is why we call this the distance formula. Square root of a squared plus b squared. But what you're going to see more often for the distance formula is instead of a squared, you would say x2 minus x1 squared. And instead of b squared, you'd see y2 minus y1 squared. This really is the distance formula. x2 minus x1 is your delta x. y2 minus y1 is your delta y. Oops, I don't want to do that. Which is why it's really cool. Well, we'll go to the next slide. Hold on. How far did the robot travel in 2 seconds? We just had distance equals, I can say delta x squared plus delta y squared, right? So if I substitute what we found in the previous numbers, let's see, number 3 was the delta x, so that's 20 squared. Number 4 was the delta y, 30 squared. Add those together, take the square root. Oops. I get 36.06 feet. That is how far the robot traveled between those 2 points, between the red point and the blue point. So we know that if we let the robot continue with the motion, it's going to hit the wall, right? So we need to discuss this a little further so we can figure everything else out. So I know your classwork doesn't have much else left in it, but we need to discuss a few more things so you know how to do your problem set. Okay? This is where linear equations and algebra. I'm going to do a little bit of review. So let's talk through a few other random questions. So when we talked about the location of impact based on the diagram, now that we're drawn on an actual coordinate plane, let me get the thicker marker out. Like, I know I'm starting, actually, the line goes straight through the origin. Now, this coordinate plane is not drawn to scale. Okay, we're supposed to be 2,000 there, and 1,000. Wait. Nope, I'm backward. Oh no, I'm right. We're good. So we're definitely going to have a point of impact up here somewhere before it reaches the right wall. Okay, we're going to definitely hit the top wall. Because if the line's extended, that's where it's going to intersect first. So where will the robot hit? We figured that out pretty well just by using our slope. Right? We already calculated that, so we don't necessarily need to calculate it again. Like every time we go up 300 over 200, up 300 over 200, up 300 over 200. And that's what I just did. You know, I went 300 times, goodness, how many times does 300 go into 1,000? It was 3 1/3 times. So we can go up 3 1/3 times, and for every 3 that we go up, we go over 2. So if we can just say that we went up 300 1/3, we're going over 200 every time. So that would be 666 and 2/3. So that's how we got that. When I did the calculation, I used the linear equation, except I used it in the right way. There we go. We knew the y-intercept was 0, so my linear equation is y equals 3/2 x. I knew I hit the y, y equals 1,000 first, because right there is at y equals 1,000. So I just plugged 1,000 in, and I solved for x, and that's how I got 66 and 2/3. Okay, where would the robot be at time equals 23 seconds? It wasn't that bad because we knew we were traveling at 18 feet per second. So if I multiply that 23 by 23 seconds, that gives me 414 feet. 18 times 23. Yep, 414 feet, which is pretty cool. That's where the robot's going to be at 23 seconds. More random questions. What can we use to find the location of the impact? I did that. Sorry, this is going in a really awkward order. The location of impact we decided was the top of the warehouse because we have a linear equation. So at the top of the warehouse, that was y equals 1,000, and I used my linear equation. I can multiply both sides by 2/3. I think I did that. And I've got x equals 666 and 2/3. Pretty cool. Now, what was needed to calculate the speed? Speed is also your rate. Distance equals rate times time. Distance over time equals rate. So if we knew the distance and we knew the time that it was traveling, then we could figure out the speed or the rate, correct? What were the, let's see, I'm just going through the random questions. What were the units of speed? Well, it's this little robot. What's it doing? It's traveling in feet, and everything is calculated in seconds. So rate or speed equals feet per second. How far did the robot travel between the given 2 points? Well, we had 2 points, and we made a right triangle out of them. And distance, d, is your hypotenuse, which is c in the Pythagorean theorem. A squared plus b squared equals c squared. A, b. If I'm solving for this value, which we're going to call d now, which is distance, I take the square root of both sides, and I'm left with a squared plus b squared equals d. And a squared we can calculate. Let's see. We're going to say x1 comma xoy and x2 y2. So I can calculate a by just saying x2 minus x1. So right here, x2 minus x1 gives me my delta x, plus y2 minus y1. Now it does not matter which order you go in. So here we have y2 minus y1 gives me my delta y. And that gives you your distance. Once you can calculate through that, you get your distance. How long did it take the robot? So we got a distance of delta x was 20 squared plus delta y was 30 squared. I've calculated this so many times now. Got the numbers memorized. 36.06 feet. And we knew it took 18 seconds to do that. So if we have 36.06 feet divided by 18 seconds, that gives us about 2 seconds. Yep, 2.00. I'm sorry, that's 18 feet per second. Are you guys catching my mistakes? Because distance over rate equals time. Cool? Now I hope you're still watching, because this is a question that's going to come up in your problem set. Where did the robot start its motion? At time equals 0. Okay, that's where it's going to start, at time equals 0. So at time equals 1, we were at 30:45. Our slope, our change in y over change in x, is 3/2. I'm going to simplify that again to 1.5 over 1, or 15/10. I know. I don't mean to confuse you, but we can also say this is 30/20, which I can divide both by 2 and get 15/10. That sort of helps with how I've drawn my scale. Each one of these blocks is worth 10, etc. So if I'm right here and I want to move back to the origin, I'm going to go down 15, 5, 10, over 10. And that was 1 second, right? Down 15 over 10, down 15 over 10. But here we're at this length here is 2 seconds. So I went up 15 over 10, up 15 over 10 in 2 seconds. And this is at time equals 1. Where was I at time equals 0? So we're going to go here and go down 15 over 10, right there. At time equals 0. My ordered pair is 10, 20, 10, 20, 30. At time equals 0. Very cool, huh? Now what is the distance 20, 30 to the wall? Let's do that again. Hold on. So we're trying to get the distance from 20, 30 all the way to the wall, and we're saying where we hit the wall. And we hit the wall at 666 2/3, 1,000. So that's what we're going to do with our distance formula. Change in x minus 20 squared plus change in y, 1,000 minus 30 squared. I'm going to push pause and calculate this. Okay, distance equals 1,165.8 feet. And we have a rate of 18 feet per second. So if I divide this, I can tell you how much time it will take. Divide by 18, 64.7 seconds to hit the wall. Cool? That's really it. That was a lot. We did a lot of these problems twice, but sometimes that helps. Seeing things again, no big deal. Your problem set is very, very similar to the lesson, so I hope, since I did everything twice, it helps you understand. Good job.